Hello everyone, welcome back to another episode of Solving LeetCode Hard Questions. Today's question is Russian doll envelopes. The question is as follows. You're given a 2D array of integers envelopes where envelopes I represents the width and the height of an envelope. One envelope can fit into another if and only if both the width and height of one envelope are greater than the other envelope's width and height. Return the maximum number of envelopes you can Russian doll. In other words, put one inside the other. And note that you cannot rotate an envelope. Let's look at some examples. In the first example, the envelopes are 5, 4, 6, 4, 6, 7, and 2, 3. And the output is 3. This is because you can fit the envelope with width of 2 and height of 3 into 5, 4, and then fit 5, 4 into 6, 7. And that's 3 envelopes together. In the second example, all the envelopes have a width and height of 1. And the output is 1 because we require the width and height to be strictly greater than for one envelope to contain the other. How do we solve this? Pause here if you like to think independently for a moment. A natural first step is to reduce the 2D problem to 1D. We can do that by sorting by the widths first. Looking at the example from the previous slide, after sorting by its first element, we get the sorted list as 2, 3, 5, 4, 6, 4, and 6, 7. Now we're guaranteed that the widths are increasing. The next step is to make sure that the heights are increasing too. In other words, we want to find the longest strictly increasing subsequence in the heights array. 3, 4, 4, 7. However, there's one caveat. What if the heights are strictly increasing, but the widths are the same? For example, 6, 4, and 6, 7. 6, 4 does not fit into 6, 7 based on our requirements. To resolve this, we need to sort the list by a secondary index, its height, in decreasing order. So, flip these two elements, and the new heights array are 3, 4, 7, 4. This way, we prevent the situation where the heights are strictly increasing, but the widths are the same. We've successfully identified the subproblem after sorting, which is to find the longest increasing subsequence in heights array. Given an integer array nums, how do we return the length of the longest strictly increasing subsequence? The naive approach would be maintaining a list of every possible subsequence. Let's look at the example where nums is equal to 10, 9, 2, 5, 3, 7, 101, and 18. To start, we have the number 10, so subsequence 1 will have element 10 inside. Then we have the number 9. 9 cannot be added to the first subsequence, but we should build another subsequence in case in the future the longest subsequence starts with 9. Moving on to the third element, 2. 2 cannot be added to any of these two subsequences, but again, to make sure we don't miss the case where 2 is the starting subsequence of future elements, we need to create a new possible subsequence. Then we have the number 5. 5 can be added to the third subsequence. Then we have 3. 3 cannot be added to any of the current possible subsequences. However, we can create a new possible subsequence with the element 2 and 3. Next, we have 7, which can be added to subsequence number 3 and number 4. Next, 101, which can be added to all subsequences. And now we're at our final element, 18. 18 cannot be added to any of the current subsequences. But again, there are new subsequences that can be made from this element 18. And they are 10, 18, 9, 18, 2, 5, 7, 18, and 2, 3, 7, 18. So looking at all these possible subsequences, the one that yields the longest length are these ones, and they have a length of 4. So the output is 4. In summary, this is what we did in a naive approach. If the item can be added to the end of the sublist, add them to each sublist. If not, start a new sublist from the original sublist till where the number can be added. As you can see, keeping track of many sublists increases our time complexity by a lot. So can we do better? Can we stack the sublists somehow? And how do we stack them? Our goal is to maximize the subsequence length. So given a subsequence length of x, can we try and minimize the last value? Let me explain what I mean in the next slide. Using the same example from before, let's look at the problem in a different perspective. What if I asked you to find all the increasing subsequences with length of 2? Then we cut these options by length 2. All these subsequences will work here, but some options are clearly better than the others. In this case, the subsequence 2, 3 is better because it gives us more potential to build longer subsequences in the future. Similarly, if I ask you to find all the increasing subsequences with length of 4, there are many options here, but the subsequences that end with 18 has more potential of building longer future array. So instead of storing all these different subsequences, we can just store the element that will give us the most potential to build longer future array at each index. And in this example, it's 2, 3, 7, and 18. The approach we're using here is dynamic programming. We would first binary search for the index to replace the element in the longest increasing subsequence list. If the index is already at the end, we append this element using the same example, but I added 2 more elements at the end. The resulting longest increasing subsequence is 2, 3, 7, 16, and 20, with a length of 5. Note that this is not the actual longest increasing subsequence, because as we can see, 16 is after 20. But this doesn't matter for us because we only care about the length. And the number 16 here just means that 16 is the smallest value if we restrict the increasing subsequence to a length of 4. And since 16 is the smallest value, it will allow us to build longer future array. Putting everything together, this is a pseudocode in Python. First, we sort the array by sorting its width in ascending order, then its height in descending order. The next step is to find the longest increasing subsequence from the heights. We'll first use binary search to find the index where a smaller value needs to be put in. If the index is already at the end, then we append it to the longest increasing subsequence list. At the end, we return the length of this list. The time complexity is O of n log n because the first sort will take O of n log n, and in the second half of the block, we're doing binary search, which is log n, for every element, which is O of n. So that's also O of n log n. The space complexity is O of n for the list array. That's it for today. Thank you for listening, and see you next time.